Hi, and welcome. This is going to be a short video on an interesting algebra problem. I've recently seen a few videos going around where you're given perhaps x plus 1 over x is equal to some value like 6, and maybe you're asked to solve for x to the third plus 1 over x to the third. Or you're given x squared plus 1 over x squared, and you have to solve from some other higher power. And I thought it'd be interesting to show the general case. So here we start with x plus 1 over x is equal to some constant k, and we don't care what that is. And we want to show how a general rule for any higher power of x. And we're not going to solve for x to do this. So we're gonna label this sequence of expressions. So we'll call f of n, we'll label that as x to the n plus 1 over x to the n. And so just to show how this works, f of 0, for example, is x to the 0 plus 1 over x to the 0, which is obviously 2, regardless of where we started. And f of 1 is x to the first plus 1 over x to the first, or x plus 1 over x, which is k. This is our definition. And f of 2, which is x squared plus 1 over x squared, excuse me, we don't know yet, but we will find out. And so on. And we're going to do this by considering building up a little algebra here. So first we'll look at f of 1 squared. And we're looking at this of the algebraic definition, not that f of 1 equals k. So we think of x plus 1 over x squared. And just simple squaring a binomial, it's not that hard to see that you end up with x squared plus 1 over x squared plus 2. And let's get my laser pointer here. And I've color coded this to show. So x squared plus 1 over x squared is f of 2. That's what we defined before. And 2, if we remember, f of 0 we showed was 2. So f of 1 times f of 1 is f of 2 plus f of 0. And we got this by just simply expanding the binomial here. So if we rearrange a little bit, move the f of 0 over to the other side, then we see that f of 2, which is x squared plus 1 over x squared, is equal to f of 1 times f of 1 minus f of 0. Now, since we know f of 1, f of 0 already, we can just substitute in that this is going to be k squared minus 2, if we wanted f of 2 directly. But we're going to look for a general rule here. So we're going to consider f of 1 times f of 2 now, algebraically. So we're just playing around a little bit right now. So here we have these two binomials we're going to multiply. This is f of 1, and this is f of 2. And when we multiply them, and we rearrange the terms a little bit, and this is just simple binomial multiplication, we get x cubed plus 1 over x cubed plus x plus 1 over x. And we see that this, which is in blue, is the same as f of 3, and this is the same as f of 1. So f of 1 times f of 2 is f of 3 plus f of 1. And rearranging, since we'd like an expression for f of 3, we move the f of 1 to the other side, and we see that f of 3 is f of 1 times f of 2 minus f of 1. Now, we already have f of 2 and f of 1 from previously, so if we wanted to, we could write out an expression with k here. But if we look at this part here, maybe we're starting to see a pattern now, and it'd be nice to see if there is a general pattern here, because this was a little bit familiar, similar to the one we had before. So why don't we try get a little inspiration from this, and we're going to try a general case. So what if we take f of 1 times, and now we're going to use a very general expression here, f of n minus 1. And the reason I start with f of n minus 1 instead of f of n, you could do it with f of n, is because we saw that like we took f of 1 times f of 2, we end up with an expression for f of 3. And we end up with one higher. F of 1 times f of 1, we end up with an expression for f of 2. So here we're hoping we'll end up with an expression for f of n. So here we have, again, binomial multiplication. F of 1 is x plus 1 over x, and f of n minus 1 is x to the n minus 1 plus 1 over x to the n minus 1. And if we expand that, and rearrange the terms, we get x to the n plus 1 over x to the n, and x to the n minus 2 plus 1 over x to the n minus 2. And we see that this is simply f of n, and this is simply f of n minus 2. So this is f of n plus f of n minus 2. And we notice that we want to rearrange things again because we're looking for f of n, so we can just move this over to the other side. And we get this expression here where f of n is equal to f of 1 times f of n minus 1, that's just this, minus f of n minus 2. We move that over. Now remember, f of 1 is k, so in this case we can just substitute in the k, our starting value. And so we get f of n equals k, a constant, times f of n minus 1 minus f of n minus 2. And if we notice here that this is a recurrence relation with two initial conditions, since we have f of 0 and f of 1. So I'm not going to go into the background on recurrence relations here. So that's something you can look up if you're interested. I'll give you the solution to them, but these are well studied, and there's a rather easy way to solve these once we have a recurrence relation. So this is like similar to the Fibonacci series, right? Where the Fibonacci series in this case would be f of n equals f of n minus 1 plus f of n minus 2 with no multiplier here. So that would be the Fibonacci series, for example. And we'd have initial conditions 1 and 1. Or 0 and 1, depending on how you are counting. So this is a simple recurrence relation. And in fact, it's called a second order linear homogeneous recurrence relation. That's the full name because there's no squared or higher order terms. It's second order because it depends on two previous terms and has constant coefficients. So this has a really nice way to solve for it. So what we do is you get something called the characteristic equation. And this is actually taken from the coefficients of the two recurrence terms here. So we're going to start a new variable t, which is going to be our solution. And you have t squared, and it's going to be minus the coefficient of this one times t minus the coefficient of this one, which is just 1, and that's the constant. And then, so we solve this for t, and this is the two values of t are going to, combining them is going to give us our solution. And like I said, I'm not going to go into the background. This is just how you solve recurrence relations, and you can look that up. There's lots of information about them. So using quadratic formula to solve this, we have an expression for the two values of t, the two solutions here, which is going to be k plus or minus the square root of k squared minus 4 over 2. So this gives us our solution directly. There's a few minor complications. So we're going to say when k is greater than 2 to avoid adding complications. It's a little bit different if k equals 2 and there's one root, and we're going to skip imaginary values for now. So for k greater than 2, then this will give us the following form. So this is the general form when you're solving a recurrence relation and you have two distinct real roots. Then it's going to be some constant. So f of n, the general form, will be some constant times one of the solutions to the nth power plus another constant times the other solution to the nth power. And these two constants, we find them by using our initial conditions. That's how we find what a and b are. And we have our t1 and t2 because we solved that characteristic equation. So here are our initial conditions, so we can use these to find a and b, and this is just really simple algebra. And if you just sort of plug in 0, 2 equals and put in 0 for n, and then 1, do the same thing, simple algebra will give you that a equals b equals 1. So it's quite simple in that case. So this gives us the following expression. So this is a closed form for finding x to the n plus 1 over x to the n if you're given x plus 1 over x, where k is x plus 1 over x. And it looks weird because you're going to have these square roots in here, but what ends up happening is as long as you're starting with a integer, a real number, these will always cancel out. So I'll just show a really simple example, but this is the general formula. So here's a example problem. So if x plus 1 over x equals 6, then find x cubed plus 1 over x cubed. Now, you could do this much easier by hand because this is a very x cubed plus 1 over x cubed is small enough that it's not worth using the whole big formula. So, but you can confirm it by kind of doing it by hand. But I'm going to show using the formula as how to do it. For much higher roots, the formula is going to be easier. So k is 6 in this case. So plugging in the formula, this is our n is 3 and k is 6. So simplifying, then each of these expressions becomes 3 plus 2 times the square root of 2, and this is 3 minus 2 times the square root of 2. And here we just have two simple binomials to expand. And what's going to end up happening is all the square root of 2 terms are going to cancel out. And when we expand them, for example, the first one, we end up with 99 plus 70 square root of 2, and the next one we end up with 99 minus 70 square root of 2. And you see how these are the rational term will be the same, and the irrational terms will cancel out. And here we end up with 198. So that is an example. Thank you. I hope that was interesting.